Well, thank you very much. There's not many people here. There never is at this time. But you know what? With jet lag, I didn't wake up till 3 o'clock, so I probably couldn't have done the talk before now anyway. Oh, by the way, that's not the title that was advertised, but it's the same talk. I just like this title better because it gets more people in the room, as we can see. I'm James. I used to work for ThoughtWorks. You may have heard of ThoughtWorks. You may have heard of Martin Fowler. I don't anymore, and now I work for Codurance, which is a much smaller company, but I'm really enjoying it. Fun fact about me, I have a thing called face blindness. You all look exactly the same to me, literally, apart from those of you that have beards. This is what I'll be talking about. This is about quantum computing, and it's about cryptography. And hopefully, you might learn something. Somebody in the room might teach me something. That sometimes happens. So why am I here in Russia? So in the summer, in June, I was at a conference in London, and as you can probably guess from that photo, it was a little bit warmer then than it is now. And afterwards, I spoke to Leo and Dora, and they said, hey, do you want to come to our conference? That talk was great. Can you do a longer version of it? And I was like, yeah, brilliant. Where is it? And they went, Siberia. I was like, oh, okay. When? And they said, December. And I was like, oh, sure, I'll come. I didn't realize quite how far away it was, and then in between I changed my job, so I didn't know whether I'd still be allowed to talk at conferences. That's my last day at ThoughtWorks. It turns out I am allowed to talk at conferences, and I spent kind of Friday and Saturday in a quantum theme. It felt like I was in two different places at once doing a bit of time travel, because I left London at 10:30 on Friday, and I got to Siberia via Moscow. That's all I saw of Moscow, slush on a runway, and I felt like this when I got to this place eventually yesterday. And but what a wonderful building. I kind of didn't realize when I got up in the lift to the 13th floor yesterday, and I thought, hang on, this building's bigger than it was on the ground. I didn't realize it had that funny bridge thing, which I think is awesome. And then I found a hotel, and this always disturbs me when there's no floor zero. I think, come on, it's 2019. Surely we know that numbers start at zero by now. But not as bad as when I spoke at a tech conference in Porto earlier this year in Portugal, and the hotel looked like this. Not only has it got no zero, but it's also got a -1. Who built that building? That is absolutely impossible. I literally cannot go back to Porto now because of that hotel. It just scares me. And here's some photos of last night. There was a great party here, and then we all went off to a sauna. I didn't get the memo for the other speakers, so I had to go in my running shorts, but that was lovely. Apparently that's a Russian thing, so my Russian friend tells me, and I got whacked with branches in the sauna. Whew, it was lovely. That's today. My daughters wanted to see some pictures of snow, so I obliged there. And then later on, I found this nice blurry effect on my phone. It's amazing what modern phones do. And as you can see, I was getting a bit colder. And then I thought I'd take another picture of this great building for my architecture talk, which sadly I'm not doing now. Otherwise, this picture and others would crop up a bit more. So let's get on to actual business. Who in this room knows about cryptography? I'm hoping everybody knows a bit about it. So a quick 101. We'll start with a pub quiz. Do they do pub quizzes in Russia? No, okay, so that does work outside of the UK. Cool. That's me back in my ThoughtWorks days doing a pub quiz. Does anybody know who these three gentlemen are? Does anybody want to guess who these three gentlemen are? It's got a cryptography theme. No, that wasn't right, whatever you said, because no one's ever heard of these. They are called James Ellis, Malcolm Williamson, and Clifford Cox. Fun fact, this name here is hilarious in English, particularly when it's spelt like that, not C-O-X. It's not nowhere near as funny when it's C-O-X. Anybody want to guess on these two? These are pretty famous. Come on, they're guessable. Okay, they're Diffie and Hellman. They're quite important. They come back into the story later. Now, on the theme of Diffie and Hellman, can anybody guess who these three are? Or guess an algorithm that they gave rise to? RSA, well played. Thank you. They are Rivest, Shamir, and Edelman. We will come back to those gentlemen later. This is what cryptography is. We always talk about Alice sending a message to Bob. And Eve is trying to eavesdrop the message. That metaphor works really well in English. Don't know about other languages. And the key point is here. Eve needs to listen to that message in such a way that they didn't know that she listened. It isn't valuable to read the message if they know you read it. And a great example of that was during the Second World War, when the British and the Americans and the Russians had broken all the German codes, but we couldn't act on the intelligence, because if we acted on every piece of intelligence, the Germans would have known. and they would have done something different. So it was important for us to try and keep up the pretense that we weren't listening to the messages. In public key cryptography, which is what we use now, essentially it's based on any mathematical operation which is easy to do in one direction and hard to do in the other direction. So RSA is based on the fact that it is very easy to multiply together two large prime numbers, but it is nigh on impossible to work out the factors of a large composite number. And obviously we'll come back to that. And as I say there, factorizing a large number is of sub-exponential complexity. And what that means is essentially impossible. We use 2048-bit keys in RSA now. If you get the most powerful supercomputer in the world, it will take about 40 years for that computer to break current RSA keys. If you go to 3072-bit keys, if it were possible to construct a classical computer that used every electron in the universe as a computational bit, and there are about 10 to the 80 electrons in the universe, it would take that computer longer than the lifetime of the universe to factorize a 3072-bit key. So RSA is pretty safe against attack from classical computers. But quantum computers are a different animal. So who's used quantum computers in this room? Just me. Great. Quantum computers are great. I've got a photo of me standing in front of one actually, but I don't think I've got it in this deck. It looks pretty boring, to be fair. I prefer the IBM pictures. So, in order to understand what quantum computers do, firstly, just recap. I hope people know basically what classical computers do. They work with bits. Bits are zeros or ones, we usually represent them as. The picture on the left is an OR gate. What classical computers do is they take all these zeros and ones and they push them through gates, and then they might transform them into different zeros and ones on the other side. So as you can see there, that's a kind of electrical circuit representing an OR gate. If either A or B is closed, the light switches on. If they're both closed, the light switches on. That's a classical OR gate. This picture on the right, as you can see, all of these funny looking shapes are different types of gates, and they all go together. The lines represent bits flowing through and possibly getting transformed. That is a diagram of 16-bit floating point arithmetic. So that is how a classical computer does multiplication. And that's all classical computers do. They put together all these gates in many millions of sequences, and they sum up to something useful. That's essentially all they do. It's pretty powerful, mind you. Now, a quantum computer uses something called a qubit, which is similar to a bit in that when you measure its value, it always returns, it tells you it's 0 or it tells you it's 1. That's where the similarity ends. Quantum state looks a bit like this. That thing on the right, that picture represents a schematic of a qubit. The pointer up there on the right with that Greek letter that looks like a toasting fork, I think that's psi, that represents the quantum state. If it's pointing straight up where the 0 is, it will tell you it's 0 100% of the time. If it's pointing straight down where the 1 is, it will tell you it's 1 100% of the time. If the quantum state is anywhere else on the surface of that sphere, it might tell you 0 or it might tell you 1 when you measure it. But, two things, if you use that in a computation, it will use both values. So unless it's pointing straight up or straight down, it actually has both values. It doesn't have a definite value, it has both values. And then immediately after you measure it, that actually affects it. That interferes with the quantum state, and it kills the quantum state to the extent that it is then deterministically 0 or 1, depending on what you measured. Those are very important properties of the qubit. I won't go into too much detail now. And just like a classical computer, a quantum computer has gates. This is the set of logical gates that the IBM Q computer exposes. If you Google for IBM Q, you can get a free account and you can play with their 5-qubit computers. You can program them. I'm not going to go into what all these gates are. Some of them are very simple. X, Y, and Z basically transform the quantum state through 180 degrees on the block sphere picture. The only other one that I'm going to mention in any detail is the H gate, the very first one there. The Hadamard gate, that's called. It's named after some electrical engineer bloke from the 1930s. And what that does is it takes the qubit in its base state, which is the 0 state, and it rotates it through 90 degrees. So it's exactly 50% likely to give you a 0 or a 1 But as I say, then it's in superposition. It will give you a 0 and a 1 in every computation. That's the really powerful piece about quantum computers, which I'm going to go into in a bit more detail now. We need to talk about, to understand why quantum computers are so powerful, superposition and interference. So, here's my first cinema interlude. This is usually where this talk goes wrong, as it is there. So I need to do that thing with the screen, don't I? Hang on. Display preferences, please. Where's mirror displays? There it is. Oh, that was smoother than I normally do this. Oh no, go away. Are we there? Good. This end, 3D models of Ben. We've got Big Ben, medium-sized Ben, little Ben we left on the table over there somewhere. They're holding our screens and we see the results. So let's see if we can make the interference pattern at the other end of this text. Okay, what's going on there? What's the point of that experiment? So, that is called Young's double slit experiment. And that experiment was first done in the 1809, I think it was. Up until that point, people believed that light traveled as particles because Sir Isaac Newton in Principia had postulated that light traveled in particles that he called corpuscles. Nobody really challenged that for 100 years or so, until by the start of the 19th century, people were starting to believe, light actually might travel in waves. So what Young devised this experiment to show that light did travel as waves. What he said was, if I can show that light has interference patterns, then it must be waves, right? Because particles don't interfere with one another. So what's going on in there, as you can see, the very bright blob in the middle is positive reinforcement, where the waves, where the peaks and the troughs coincide. The dark patches are where they cancel each other out. So it looks a bit like that. That's a schematic of it. You've got the two slits on the left, the two waves go forward, and you can see where they positively reinforce, you get the bright spots. Where they cancel each other out, you get the dark spots. So light travels in waves, and that was 1809, and everybody's like, yeah, cool. But then quantum physics came along at the end of the 19th, start of the 20th century. And with Einstein's paper in 1905, all of a sudden, physicists were forced to accept, hang on a minute, light doesn't travel as waves. It travels as tiny particles called photons. They're weird. So everybody then said, well, hang on a minute, though, how do we get an interference pattern? As you can see in that picture, you've got millions and millions of photons going through the slits simultaneously. So they said, well, hey, okay, we're going to invent something called wave-particle duality. So photons interfere with other photons. And everybody's like, okay, yeah, I'll accept that. So that was our explanation at the start of the 20th century. All well and good. Although it feels a bit uncomfortable to just invent something called wave-particle duality. And then, in the 1940s, technology got better so that it was possible to do something that looks a bit like this, but you can guarantee that you're firing only one photon at a time through the slits, okay? And then you would think that there's nothing to interfere with. There were no other photons to interfere with, but what actually happens is that you see the interference pattern building up. So all of the photons take an interference path through the slits, even though there is no other photon traveling at the same time. So now we have to say, What is causing that interference? There's nothing there to interfere with. Now, the startling answer is the many worlds interpretation. Wheeler in the 1950s postulated, and it's now gaining ground, that actually, if you fire the photon through the slits, as we did in our experiment in the video, there's actually a finite number of paths the photon can take, because space is divided into tiny units. It's not a continuous quantity. So even though there are possibly many millions of ways the photon can go through the slits, it's a finite number. And as the photon travels, it actually goes through all of those paths at the same time in many different universes. And it interferes with all of those other photons in all of the other universes. That is the most plausible explanation for what is going on. And in fact, that is what happens inside a quantum computer. When you have superposition, which is exactly what the different paths of the photon are, those superpositions interfere with each other and give us amazing computational power, which is what I'm going to demonstrate in the second half of this talk. But before I do, a quick word about my daughter's cat. This is Clementine, my daughter. This is her cat. This cat is displaying the same emotion that cats normally display, which of course is indifference. So we decided some time ago to try and run a quantum experiment on the cat to see if we could do anything with the cat moods, to see if there could be a superposition of cat moods. And it turns out, oops, that's the wrong button. Oh God, that wasn't what I meant to do either. It turns out that the cat can have different moods simultaneously. In fact, up to 8. Superposition and interference, this diagram here, this is a circuit diagram. This is called a quantum score. The horizontal lines represent a qubit in a computer. The circular bits are representing gates. And you can see on this picture there's lots of Hadamard gates and there's lots of R gates. The R gate is a phase shift, which is really too complicated for me to explain now. That transform is called the quantum Fourier transform. Has anybody worked with digital signal processing? Has anybody heard of the Fourier transform? Yeah, a few people. What the Fourier transform does is it converts, essentially, the time domain into the frequency domain. So it helps with compression of signals when you send them over a channel. In a quantum computer, it does something very similar. Because your qubits, whilst we represented the state as a sort of single point, it's actually a wave pattern. And what this transform does, this Fourier transform, is it converts that wave pattern into a frequency diagram, really, which is really useful, as I'll show you now. And what I'm going to talk about now is what I call the elephant in the quantum room. Is that a phrase outside of English? I don't know. So in English, the elephant in the room is this big, ugly thing that's around and nobody wants to talk about it. You just kind of ignore that it's there. And in quantum computing, there's a load of really good uses for quantum computers that we're delving into. We're starting to understand how to make drugs better through quantum simulations. We're starting to understand chemistry better, which is really what the drugs thing is. And the most exciting thing is that we're starting to understand how the iron-molybdenum complex in bean plants fixes atmospheric nitrogen. Because at the moment, the world uses 3 to 5% of its entire production of natural gas goes into making ammonia for fertilizers. But bean plants do it without any energy uptake. So if we can understand how they do it through simulation, we'll potentially save all that energy. But quantum computers are being used for something called Shor's algorithm, or there will be. Now, this is, remember earlier when I said that factorizing large numbers is of exponential complexity. That's Peter Shor, and in 1991, I think, he came up with Shor's algorithm, which I'm just going to spell out on the screen. My God, there's a spelling error there, does it? That should say we are done at step 3. It looks complex. Actually, it's quite simple. That's the simple formulation of the algorithm. It's based on a bit of number theory, a bit of straightforward algebra. It's easier if I illustrate by an example. So, let's say we're trying to factorize 15. I think we all in this room can probably work that out in our heads. So, step 1, we choose a number less than 15. So let's choose 2. Is 2 a factor of 15? No, it's not. So, you basically check first, because you could get lucky. Because finding the greatest common divisor of 2 numbers uses Euclid's algorithm, which is trivial compared to other stuff. So you just check. Then we say, okay, we find the period of 2 to the x mod 15. What does that mean? Well, 2 squared is 4, 2 cubed is 8, 2 to the power 4 is 16, which is 1 mod 15. Does everybody remember modular arithmetic from their maths at school? Or university, maybe? So if you keep raising 2 to successive powers, it goes 2, 4, 8, 1, 2, 4, 8, 1, 2. So it's cyclical, and it has a period of 4. So what that tells us is that 2 to the power 4 is equivalent to 1 mod 16. So 2 to the 4 minus 1 is 0 mod 15. 2 to the 4 minus 1 factorizes to 2 squared minus 1 times 2 squared plus 1. And those are going to give you the factors, because those two numbers, 2 squared minus 1 is 3, 2 squared plus 1 is 5. Hey presto, we've factorized 15. There you go. Now, here's a more complex example. One day, must be about a year ago now, I was traveling to work and I'd been trying to get my head around Shor's algorithm. So I decided to actually use it on a real number. So I picked 1,517 and I said, right, I'm going to factorize that. So, first of all, on this first sheet, you can see I picked 4. And that's 4 in column C being raised to the successive powers. And then in column D and E, it looks like I've taken it modulo 1,517. So you can see it goes 16, 64, 256, 1,024, then it comes back down again. So that's going to be periodic with a maximum period of 1,517, right? Because there's only that many numbers. So if we scroll down and 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 down, eventually we see there. The period of 4 is 90. So what that tells us is that 4 to the power 45 plus 1 and 4 to the power 45 minus 1 are multiples of the factors of 1,517. Great. So if we come back up here, we see that 4 to the 45 is there, but column C's gone blank because it overflowed there. So that was no good for my calculation, right? Because I need actual integers. So I carried on trying. I tried 16. And then you can see that period is 45, which is a lower number, but that's not helpful. It has to be an even number for us to use it in Shor's algorithm, the period. So that's no good. Then I tried 5. By this time, you can see I've added column F to make it easier to scroll down and find the period. There it is. Its period is 180, which is even worse. I tried a few different numbers. That one overflows pretty early. That one overflows pretty early. Eventually, I think I got to 10, and I was quite excited because its period was very low and I could see it didn't overflow. But damn it, that's an odd number, so that was no good. And then finally, 14 worked for me. Don't know why. There's probably some number theory stuff that you can work out why this period. I also noticed that all the periods are multiples of 45 somehow, apart from this one. Again, don't know how. Must be something to do with this number. But there you go. The period of 14 is 24. Now, that overflows, but the crucial point is that 14 to the 12 is that number, which does not overflow in Google Sheets. So I've got an integer I can work with there. Just a quick side note, when I did this talk in London, they insisted I didn't use the Google Sheets. That's from this photo earlier. They said, download it into an Excel sheet because you can't trust the Wi-Fi. So I did that, and then I looked at the spreadsheet, and Excel overflows 1 bit less. Excel has 32-bit overflow. This has 64-bit. So I was standing on stage going, I'm sure this worked at home. Let's go back to this. The point about that is, so here we go, just run through. We're factorizing 1,517. Yeah, there's 10. It's an odd number. We chose 14. So 14 to the 12 minus 1 is that big number, which is a multiple of 37. 14 to the 12 plus 1 is that big number, which is a multiple of 41. So that's how you factorize a big number. And we find that 1,517 is 37 times 41. Great. Where is the magic in that? That seemed pretty complicated, right? That seemed like a fairly long way around to factorize numbers. And in fact, that algorithm, when you execute it on a classical computer, is not the most efficient way to factorize a big number. But the magic is there. in step 4. Use the quantum period finding routine, which I'm now going to go through. Because if you think when I was showing you that spreadsheet looked fiendishly complex, because it is. It's got millions, potentially, and millions of computations in it. But we don't care about all those big numbers. We don't actually give a shit what those numbers actually are. All we care about is finding the period of the number. Now, if you think back to what I said about the quantum Fourier transform, that's exactly what the quantum Fourier transform does. It will take the thing looking like all those big numbers and transform it into the frequency domain so that you get a wave pattern that actually resembles the periodicity of the function. So the way it essentially works is, I have a quantum register. I put all of my qubits into superposition. So to factorize a 2,000-bit number, I would have a register with 2,000 qubits in it. I put them all in superposition using the Hadamard transform, and then I do 2 to the power of that register. The quantum computer will then calculate all of those numbers simultaneously in that spreadsheet. It will do those calculations in parallel universes. Now, if you read David Deutsch's paper on the subject, he believes that Shor's algorithm is proof that the many worlds theorem is correct over the other interpretations of quantum physics. So, that's the power, that's the quantum magic. By using the quantum Fourier transform and by examining the periodicity of the function, we can get to that period number, that 24, without doing all of those computations in this universe. So, it reduces what is a sub-exponential complexity algorithm to polynomial complexity, which means it will be broken, it will be fixable. So, if you're interested in how to actually perform the algorithm in code, that's my GitHub. Please go and have a look if you wish. I implemented Shor's algorithm using Q#, which is Microsoft's language. It's a free download. You can go to Microsoft's website, download Q#. It gives you ways of programming quantum computers. And then that output was on my old Mac. Oh, this Mac, actually. Yeah, my old one. I've run that on the quantum simulator, which sits on your computer. It's of limited use. It can only do up to about 20 qubits worth of useful computation, but it teaches you how to program. If you want to see a better implementation, this is my old colleague, one of my ThoughtWorks colleagues, Andrew. He and I conspired on this. He was a grad, so he was a young person that can get his head around these things better than an old guy like me. And he wasn't working on any projects, and I was in the office with him in Manchester, and I said, hey, read this book, and I gave him a book on quantum physics and quantum computing. I said, read this and implement Shor's algorithm for me. And I thought he'd come back to me like about a month later and ask questions and stuff. As it was, I was on the train back to London that night, and he sent me this message saying, I've done it. And it took that long, an hour and a half to factorize 35, which is an illustration of how complex it is in a classical computer. So, is RSA dead? And this is the question that we in the quantum community are asking increasingly. What do we need to care about this right now? Well, I won't go into the detail of why, but to implement Shor's algorithm, you need about 3 times as many qubits as the size of the key. So for a 2,000-bit key, you need about 6,000 qubits. Okay, the biggest known computers at the moment have around 100 qubits in them. So it would seem that the actual day when RSA dies is some distance off. However, a few weeks ago, Google claimed quantum supremacy. Now, this is a thing that has been talked about for a while. Quantum supremacy is when somebody has a real-world problem which is solvable more efficiently in a quantum computer than any current classical computer. And Google claim they've done that. IBM are disputing that claim, so are Rigetti. But hey, the fact that it's in the news says to us that more investment is coming into the quantum world, and I happen to know that the UK government is investing a lot of money in quantum projects, and I've been involved in some of that. So perhaps the speed of innovation is going to speed up. At the moment, it's a problem with material science. The physics works perfectly. The computing languages are there. What we can't do is make stable qubits or in any great quantity. So what do we do when RSA does die? Well, I'm going to go through some of this in a bit more detail in a moment. The most exciting thing for me is something called BB84, which I'm going to demonstrate, which is a quantum key distribution method. And that is provably 100% safe, and I'll explain why in a moment. So that will be the way that we will communicate in the future, I think, and it's being worked on now. There are some algorithms that are claimed to be quantum safe. There's something called RLWE, which Andrew told me about, and those other things there. They're supposedly quantum safe. I say supposedly because actually nobody's found an algorithm yet of polynomial complexity in a quantum computer to decrypt those things. But that's not to say that they don't exist, as Gödel's theorem tells us. And there are some resources there if you're interested. I'm told that the reason why we're not using RLWE, for example, in our browsers is because there's a performance hit. We could use it today, but it would slow down our browsing experience and it would slow down information exchange. So people aren't using those post-quantum algorithms yet. So, BB84. There's RLWE mentioned. I meant to take this slide out. It shouldn't be there. Anyway, RLWE, it's a bit like RSA, but it uses an array of polynomials instead of a single number as its key. That's why it's supposedly safe. Why did Amazon send me all this packaging? Does Amazon deliver stuff in Russia with like a box this big for a thing this big? They do in the UK. I don't know. Again, I don't know if that's the case worldwide. I'll show you a quick video that illustrates exactly why Amazon sent me that stuff. Clementine's cat, and as you can see, she wants to get inside. Girls, does one of you want to empty this box out just to show Amazon's packaging? What was it they sent us through the post? Well, it was these 3 tiny pieces of polarizing light filter. Okay, now let's run an experiment. Girls, you take one, Clementine, take another. You take those. Take them over to the window. Okay, so now the girls have got 3 light filters. Clementine's got 2, and Felicity's got 1. Okay, so now Clementine, if you hold 1 light filter up to the light, that's it, that's good. Now, hold it so that it's facing right towards me. That's good. Now, bring the other light filter up, Clementine. And that's it. Now, they're at right angles to each other. You can see that where they're overlapped, no light is going through. Rotate it round again, so it's the other way around now. You see that when they're in the same orientation, it still lets half the light through. So now, if you put them together the other way around, that's it. Hold them tightly against one another. That's it. No light is getting through. One of the filters is stopping all the light, the other filter is stopping all the rest of the light. Now, Felicity, get the other filter and hold it in front, so it's touching. You can see still nothing's coming through the 2 filters that are touching. And on the back, please.
Got any more water?
Nothing comes through the 2 filters. Now, slip it in between 2 filters.
Thank you.
That's it. Brilliant. Now twist it. Twist it towards you. Twist it towards you and make sure they're tight at the top. Hold it there. Fantastic. Now you can see what's happening. Where there's 1 filter, some of the light stopped. Where there's 3 filters, some of the light stopped. Where there's only 2 filters, all of the light is stopped.
So, what's going on there? That seems a little bit counterintuitive. Where 1 filter stops half the light. 2 filters together stops all the light. But when there's a 3rd filter in between, some of the light gets through again. So that feels counterintuitive. How is that, what's going on? Well, it's all to do with the orientation of those pieces of Polaroid filter. The light travels as photons, as I said earlier. On the left there, those are representing photons, those arrows. Photons have an orientation. They can be thought of to have an orientation in space. So, the first filter there is aligned vertically. Now, any photon that is perfectly aligned vertically will always go through the filter. Any photon that is perpendicular to the filter will always be stopped by the filter. However, all of the other orientations will go through some of the time, based on how close they are to the vertical. But when they go through, they get altered. Every photon that goes through is now pointing straight up or straight down. So the filter doesn't just stop things going through, it changes their orientation. That's a key thing about the way that they work. So then when it comes to the second filter, which we placed perpendicular to the first filter, as I said, now that they're all perpendicular to it, none of them get through. So that's why the two filters together stop all the light. But then when we introduced the third filter, and you could see when my daughter was rotating it, it was letting more and less light through. And that's because when we introduce it at a 45-degree angle like that, the first filter stops half the photons. Now the second filter stops half the photons, half of the remaining photons, but it twists their orientation around to 45 degrees. So that now when it hits that third filter, half of them get through. And it changes their orientation as well, but that doesn't matter. Our eyes don't see the orientation. So 12.5% of the light gets through. Now why is that important? Well, because BB84 uses that property of photons to encode the keys. The fact that you cannot examine the orientation of a photon without potentially changing it is absolutely key. So, this is the way it works. Alice is sending a message to Bob. Now, you have to have a key which is longer than the message itself, right? Which is not hard to do, right? So whatever the length of the message, you need to invent a key that's longer. She either sends zeros or ones in one of the two bases. So either it looks like this, as a 0 and a 1, or it looks diagonal, like that. Bob doesn't know whether to measure it in this basis or the diagonal basis. Okay? So, there you go. She sends the key. And that's the key, the zeros and ones on the bottom. And she chooses a random orientation in which to send them. Okay? So there you go. So that's how she sends the key. The bottom line there is representing photons. She sends them one at a time and Bob has to detect them, right? Bob doesn't know whether to measure in the horizontal, vertical basis or the diagonal basis. So he chooses randomly. So sometimes he chooses the correct basis and sometimes he chooses the incorrect basis. Then Alice just on an open channel says to Bob, this is the basis I used on every step. Okay? They then throw away all the bits in the key where he used the wrong basis. Okay? And then the thing that's left is the key. Now, why is that secure? Well, because they compare a random small chunk of the key again on an open channel. So she says, this is what I sent, and he checks it to what he measured. And if it disagrees, that means somebody eavesdropped, because if Eve was listening to the key transmission, she also didn't know whether to measure it that way or that way. And whenever she chose the wrong basis, she would have changed the orientation of that photon. And therefore, with a 50% probability, she would have disturbed the photon such that Bob got the wrong reading. So, you can't stop Eve listening to the key transmission, but you know 100% of the time if she did. That is why BB84 is 100% secure, because you just simply send the key again and again until you know that Eve didn't listen to it. And if Eve listens every time, you don't send the message. So you have a guaranteed way of sending keys. And that's why it's provably secure. So QKD is being used. The first QKD network was set up in Europe, in the EU, in 2008. I think that's no longer being used. I could be wrong on that, actually. There's a Tokyo QKD network. There is a Chinese network that uses secure satellites to relay the keys. So in theory, that can go over large areas. You have to trust the Chinese satellite, which I'm not sure I do. For that. There is some work being done on methods to do this type of key exchange where you don't need to trust the satellite. I don't understand the physics of it, but it's being done. And this was at a show I was at a couple of weeks ago in London. This is a working QKD network using fiber optic cable. There's a consortium of companies in the UK that are working with BT to use the public BT networks, the infrastructure to send quantum keys. So that is being worked on and it's being commercialized. So that is the future of secure communications. I'm going to finish with a brief history lesson. You may remember these gentlemen from the start of the talk. I think most of you probably heard of Diffie and Hellman and RSA, but probably wondering who the English guy with the silly name was. So Diffie and Hellman published their paper in 1976. This was the first time anybody spoke about a public key exchange methodology. RSA came around in 1977. That's the known history of cryptography. But in 1997, the British government told us that those three men, Cox, Williamson, and Ellis, were using RSA for some years before that. The British government was communicating using RSA before RSA was known. Now, why is that significant? Because I guarantee you now, because I've been told this by people that work at GCS HQ, the British government, the American government, the Chinese government, the Russian government, all the major governments are keeping all of our RSA traffic right now. Every time you send something on RSA over a public network, it is being harvested and it is being kept. So if you care about that message not being decrypted today, fine. If you're worried about what it being decrypted 5 years or 10 years from now, it will be. So my point is, we need to start caring as tech leaders about using post-quantum cryptographic methods right now. Thank you very much for listening.